My name is Matthew Vowles, and the talk is called Machine Learning and Causality, the Emperor's New Clothes, or a Better Analysis Pipeline. So this talk was really motivated by a recognition for the fact that in psychology, we don't just study psychology without leaning on some philosophy of science and some methodologies for undertaking statistics. And so it was a recognition that to some extent, specialization can be a little bit dangerous, to the extent that where we might be reading lots of psychology papers, maybe we're not reading that many papers on the state of the art in statistics, the most recent thoughts on the philosophy of science, and so on. So I think what's really important is that as psychologists, we are aware of what we rely on to do our research, and also what progress has been made in the things that we rely on to do our research. And so before I begin, I just want to talk a little bit about myself. So I'm just waiting to defend my Viva on integrating structure and causality in machine learning. This is a work in progress still, but we're coming to the end of this PhD. And I'm also a doctoral assistant at the University of Lausanne, so I help out with teaching psychologists statistics. I'm an affiliate member of AI at Surrey, which is a group of researchers, like-minded researchers, across many domains at the University of Surrey who are interested in using artificial intelligence for people-centered application. And I still do research on machine learning at the Center for Vision, Speech, and Signal Processing at the University of Surrey. I'm a collaborator with a causal discovery group, EPFL, in Switzerland, very close to University of Lausanne. And I'm a part-time lecturer in electroacoustic engineering at the University of Surrey. So even maybe just from looking at this, I have a range of interests. A lot of them are cross-disciplinary, or at least cross-disciplinary, but also interdisciplinary. So I want to bring these different approaches, these different ideas, different topics and domains together, hopefully synergistically, to improve the relative problems, to deal with the relative problems in each of these domains. And I started actually my research in psychoacoustics and engineering. So I worked in industry for quite a number of years, designing loudspeakers for a consumer electronics company. And I did a lot of psychoacoustic testing. So it was my first, I guess, foray into psychology and understanding how to do subjective tests. Part of this work overlapped with some machine learning, because we discussed at length the idea of having a point of sale device that would detect the age and gender of a customer and kind of have a guess at what the most optimal playlist would be to demonstrate an audio product to that customer. So for instance, the sort of playlist that you might be interested in demonstrating a product if the customer is young might be different, for instance, to a playlist for someone who's a lot older. And so that took me down the route of machine learning, particularly deep learning, computer vision, and that in turn led to some work looking at the integration of causal approaches to artificial intelligence and machine learning as well. So here are some of the papers that look at creating novel methods for causal discovery, for causal inference, but also disentanglement, so latent embeddings, taking a data set of images or a video and then inferring what the latent factors are from those videos and images. But I actually got into psychology before I got into this, because my wife is a doctor in psychology. And we had a lot of fun sort of thinking about how we could use these techniques to modernize psychology. And there's an example here of just to demonstrate that you can kind of puppet someone else's face. So this is my face on the right, and this is someone who's probably quite well known on the left. And then here is a tool that allows you to infer the sort of latent joint angles and facial key points from video. And so my supervisor also, current supervisor, well, second supervisor for my machine learning PhD, called Professor Peter Hilpert, is also interested in bringing this sort of real-time analysis, cutting-edge analysis to psychology. And so we do have some other papers in psychology which are sort of building up to this real-time analysis, where we look at approaches that exist in statistics, approaches that exist in engineering more generally, and see how we can adapt them and introduce them to the field of psychology with the aim that this enables us to answer questions that we weren't previously able to answer using the typical traditional methods that are used in psychology. And part of this, in turn, was motivated by a recognition for the replication crisis. There's a lot of open issues in psychology that are kind of worrying, but I think actually for me it's more exciting because there's a lot of opportunity to change things. In particular, there's the well-known replication crisis that gets all of the attention. But there's two things that don't get enough attention in my view, which are functional misspecification and structural misspecification. These are two things that I want to talk about in this presentation. And I want to talk about how we can deal with the latter two issues using machine learning and causality. These techniques are not intended to really deal with the replication crisis. There may be sort of a secondary effect that it does improve things, but the replication crisis kind of stands separately. And of course, there's a lot of hype in machine learning. And I want to, I guess, mention a couple of times at least, just whether or not this excitement and this hype is justified. Machine learning is very limited. It's got a lot of potential, but we don't want to oversell its potential. And similarly, causality has its own strange history, actually, and it's considered a bit of a dirty word in science and social science and psychology, even though it's absolutely fundamental to our goals as researchers, as scientists. And so I want to kind of, caveat these two appropriately, but above all, I want to bring them together to demonstrate that with these techniques, we can deal with this functional and structural misspecification issue, which I also want to demonstrate is actually very serious. And after I've sort of presented machine learning and causality as sort of viable approaches or indeed their combination, I want to propose a new pipeline for analysis for psychologists that's hopefully more holistic, more end-to-end, more complete, and hopefully more rigorous and robust. And so, spoiler alert, this is like showing you the last page of the book right at the beginning. So I really want to sort of split the research pipeline in psychology into two main parts. The first part is about theory development and how we define research questions. And the second component is about causal inference. So in this first part here, the idea is that we have our theories, our domain knowledge as experienced psychologists, and what we want to do is translate that into some kind of mathematical entity, probably a graph, a graphical representation. We want to use techniques from the field of causal discovery to inform the development of this graph in tandem with our theory, in tandem with our domain knowledge. We're not going to overwrite our domain knowledge just using these methods, but we're going to help inform how we transition from a relatively abstract theory into a relatively concrete mathematical object using causal discovery with empirical samples. And then once we have this, we can define very clearly our research questions and take those research questions into very specific target parameters, which we can again define mathematically. And these target parameters are defined in relation to this mathematical graph. Once we have that specific target parameter, we can estimate it the best we can. We can perform inference, i.e. derive confidence intervals, p-values. We can do sensitivity analysis to understand how robust our inference is to perhaps we've made a mistake in the graph, or perhaps there's some question about the definition of the target parameter. We can kind of look at how sensitive our result is to certain misspecifications using sensitivity analysis, and finally we can give a hopefully more robust interpretation than is generally done in most literature. And that brings me on to a recent comment by Anne Scheel, who said most claims in the literature are so critically underspecified that attempts to empirically evaluate them are doomed to failure. They are not even wrong. So this is super damning, and maybe I shouldn't say this, but I tend to agree with Anne that in general the hypotheses are specified so broadly in psychology it's very difficult to know really what we're actually testing, and it also makes replication very difficult because it's hard to know whether what we're replicating is the thing that was intended to be tested. So yeah, I tend to agree with Anna, and one of my hopes is that this pipeline will help us be more specific about our questions, our hypotheses, the things that we're estimating, so that we can build in some robustness to our research. So as I said, there's a bit of a crisis going on. The replication crisis gets a lot of attention. There's a very rich and detailed literature surrounding these issues, and there's a lot of purported explanations and causes behind this. For one, there's apparently a general lack of understanding concerning basic statistical concepts. This is shown kind of disappointingly frequently, that professors and researchers don't really have a firm grasp of relatively essential statistical concepts, which certainly won't help. There's a lot of unscientific incentives in academia. This is just kind of part and parcel. It's very hard to motivate good, rigorous science, because it tends often to compete against, flashy science that gets a lot of headlines. As human beings, we're interested in furthering our own careers, and that means that we're going to be pumping out publications sort of optimally in order to get our funders to fund us, or to increase our H-index, or to get an adequate number of publications per year. But these sorts of incentives are not really scientific incentives. They're kind of tangential, and they even can pull us in the wrong direction. There's obviously problems in the publication process. The publication industry is one of the highest grossing industries in the world, and there's a lot of sort of problems associated with not wanting to publish, for instance, replication studies, but there's also a lot of other issues relating to the sort of blind review process as well. And I've got lack of assumptions testing here. You could argue maybe this comes under the lack of understanding about statistical concepts, but I've kind of put it separately because actually maybe it hints more at general questionable research practices, things that maybe we cut corners on in order to promote our research or to get our research published. There's a lot of pressure to publish. And so maybe there is this sort of hint at some other sides. These QRPs, questionable research practices, are quite common as well. And I've kind of just got a list here. It goes on and on. There's lots of purported reasons and evidence that there are a lot of problems in the field and across many different fields as well. And replication tends to get all the attention in terms of, well, what we need to do is just do the study again and see if the result holds. But unfortunately, replication isn't everything. And whilst I'm a massive proponent of replication, I really do wish we did it more. It's extremely important. It can't deal with everything. And there are some things that we simply can't deal with to the extent that it may actually make things worse. We can only really deal with random sampling error. We take a sample, relatively small perhaps, and we see a relatively large effect size. Perhaps the p-value is also kind of on the high side, but we say, look, this is a positive finding. But then we take another sample, perhaps a bigger sample, and maybe that effect starts to disappear. But there are other sources of variation. Indeed, what exactly are we replicating here? As I said before, quite often the mathematical content of the hypothesis is not really specified. So you could feasibly test the same thing multiple times, the same hypothesis multiple times, but you wouldn't really be using the same model, even though you're kind of trying to answer the same research question. So this makes it really difficult. But also, what if there are problems with the original research? And this is what I mean by when I say that replication can actually make things worse, because if you've made a mistake, if your model's wrong, if your model's misspecified, and then the result may well be a result of that misspecification, a direct consequence of that misspecification, in which case doing the study again is only going to reaffirm these mistakes or reaffirm sort of flawed conclusions. And what can be wrong? Well, these are the things I was talking about before: functional misspecification and structural misspecification. These are two problems that are extremely common in psychology, and which we don't really spend that much time thinking about. As I said, replication gets a lot of the attention, but it can only go so far. So furthermore, there are kind of some attitudes in psychology that are very common. One of them is that all models are wrong, some are useful. This is a very well-known quote by George Box in 1976. And the other one is that correlation is not causation. And I kind of want to borrow an argument from Professor Mark van der Laan here, at least for the first quote. But more generally, both of these kind of adages kind of get misused as excuses for not really taking things as seriously as maybe we could take them. And to focus on this one first, as Mark van der Laan says, due to this adage that all models are wrong and some are useful, models that are so unrealistic that they are indexed by a finite dimensional parameter, think maybe a linear model, a simple linear regression, are still the status quo, even though everybody agrees they are known to be false. And so the idea here is that we start off with a model that we know is never going to represent reality. As I'll come to talk about, I think psychology is one of the most complex domains of human interest. But despite the fact that it's so complicated, we often start off with a model that we know is never going to be able to represent the complexity of that phenomenon. And so, maybe it's convenient to argue, yeah, but all models are wrong. Some are useful. We don't really need to work too hard. We can just use another linear model, even though we understand if someone were to ask us that things probably aren't linear. And the second one, as I said, is correlation is not causation, gets used all the time. I mean, I agree that it's rarely, they're rarely equivalent. In fact, causation doesn't even have to imply correlation, but it's really not the whole story. And I think if we just have this general attitude that correlation is not causation, it doesn't matter whether I have cross-sectional data, it's always going to be impossible to infer causality. And I think this is really an oversimplification, a reduction that's not helpful to us if what we're really after is a cause-effect understanding, which really is what we seek as scientists. And I'm going to sort of, I guess, wrap up this intro almost by sort of saying that social science is not rocket science. And this saying generally gets used to describe something that's very simple. Oh, it's not rocket science, it's simple, it's trivial. But actually, I would argue that social science and psychology are actually harder than rocket science. Quite often we're dealing with non-repeatable experiments in different conditions. It's very hard to get a valid replication because things change, culture changes, people change. Very hard to test, and not only that, but it's hard to actually understand both the ontology and the epistemology of the problems that we're facing as psychologists. Just as an example, when we measure emotion, it's often through some kind of complex self-reflective process, if we're arriving at it through some kind of self-report data, for instance. And really measuring emotion is very, very complicated and very difficult in a way that perhaps certain attributes relating to engineering are much more straightforward and repeatable and directly measurable. So we're faced with a really difficult problem in psychology and social science. And as such, we really need models which can handle the complexity of social science, the phenomena within social science and psychology. And so I borrow this also from, I think, Mark van der Laan's book on targeted learning, and Sherry Rose as well. And I try to convey here that this sort of outer bubble is the bubble of all possible data distributions that sort of represents the complexity of realistic phenomena. And that maybe the particular one that we're interested in is over here, the true data distribution, the true thing that we want to model and get inference on. But if we pick a traditional method, we're picking from a sort of very small, restricted family of methods here. And we almost doom ourselves to never really being able to cover the true phenomenon that we're interested in because this family is too restricted. And so if we use machine learning, the idea is that a lot of tools in machine learning are flexible enough so that we can start to expand this dashed bubble, hopefully to the point where we do encompass the true distribution. And obviously the second challenge then is to really, even if we have a family of models that can cover this true distribution, identifying the model that really does represent the true distribution is another issue, but that's kind of like a separate challenge. The first challenge is really, starting with a family of models that even in principle can model the true distribution. And so at the moment, to sort of wrap up the intro, I feel like our kind of, the paradigm for research in psychology is kind of as follows. We pick a wrong model, a model that we know is false, a model that we know is never going to represent the complexity of the problem that we're interested in. This actually generally guarantees us significance. So if we have enough data, we generally always get significant results, even regardless of whether or not the effect is large or small or even null, i.e. the effect we're interested in is zero. We always get significant results because our model is usually going to be biasing our effect size somewhere off zero. The idea of it being bang on zero is very small. And so we just really need to keep collecting enough data to guarantee that we get our publication. And of course, when we submit our paper with our significant results to reviewers, they might just accept it straight away, in which case you get a publication, or they might ask you to try another model that you know is kind of the wrong model, i.e. it's probably another linear model with some arbitrary inclusion of control variables. And as I'll come to show, we really need a smart way of including those control variables that's informed by our theory and our mathematical representation of that theory, probably some kind of graph. And so, you know, we sort of keep going through this loop until we get publications, but of course, this really doesn't result in self-correcting science. It only really results in science which confirms our prior beliefs, our prior expectations, the expectations of the reviewers, for instance, who just keep asking you to try models which might be sort of all arbitrarily wrong, but which eventually yield results which they're not too surprised or not badly surprised with, you know, that it's a result that they expect or want, maybe even subliminally, but nonetheless, and then they accept the paper. So we need a different way of doing things. And the two problems that I would argue are the causes of these issues are functional and structural misspecification. Here is a very simple demonstration of functional misspecification. Most linear models allow us to measure correlations between variables, and correlation itself is a linear kind of approximation to statistical dependence. It has its own sort of nonlinear quirks to it, which are quite interesting, which I won't get into, but really these sort of graphs are here to convey the fact that for all of these sort of nonlinear relationships, the correlation is very close to zero, even though you can see a very strong statistical dependence there. And this should be obvious, and I think that most, I guess, psychologists' gut reaction to this would be, well, you know, for this one, for instance, all you need to do is take a quadratic function of x, and then take the correlation between the quadratic function of x and y, and then you may get, you know, what you want, so to speak. But the trouble with this is that you have to know that this is precisely quadratic, otherwise, again, you're sort of biasing things according to your own intuition, your own expectations, and there may be absolutely no reason to expect that any complex psychological phenomenon is precisely linear or precisely quadratic or precisely cubic or even any precise sort of combination of those things. And so our estimates are kind of at the whim and the mercy of our own impositions. And quite often our theories also in psychology don't dictate these relationships. So they're not kind of specific in that way. And there are other ways to measure statistical dependence, which are more general. So for instance, I've included here as an example mutual information, which you can see captures the dependence between these variables. This last one is kind of an exception because actually knowing which of these blobs doesn't help you understand. So say knowing which of the two halves on the x-axis you are in doesn't help you know which of the two halves on the y-axis you are in. So here the correlation is zero, the statistical dependence is zero, doesn't really get you anywhere. But clearly in these other three, there's an assumption of linearity would be sort of a gross misspecification of the functional form relating the x variable to the y variable. And so really the bottom line here is that we shouldn't be making assumptions about the function. If we're not sure what that function is, you know, we have to have some very strong kind of priors for really specifying this and getting it right. And this is especially true when we know that this function is going to be complex. So instead, we can maybe leverage a lot of the progress in machine learning, and there's an awfully large library of methods that we can pick from, and we can even use combinations of these. So random forests, support vector machines, neural networks, gradient boosting machines. I've got here ensembles, which is maybe a nice approach because it leverages the sort of the strengths of various sort of the best of all kind of all of these individually. And you know, these will kind of approximate that function from the data themselves. And of course, whether these functions generalize, whether or not we're overfitting, these are all serious concerns. And that's why I've kind of got this sort of the emperor's new clothes here. There's a lot of hype about what machine learning can do or can't do rather. And so it isn't a simple thing of just using the latest model and hoping for the best. It does require some careful thought, but nonetheless, this is a way to at least to use again, Mark van der Laan's words, to let the data speak, to not really impose any unreasonable assumptions from the very first step of our analysis. So that was really all I wanted to say about functional misspecification. It's a huge topic, but I haven't got time today to go into all the details. So now I'm moving on to structural misspecification, and this is really to do with causality. And I'm going to kind of use these terms interchangeably. When I say it's a causal kind of structure, it's the same as me just saying a structure. It's some structure that's sort of informed by our own domain knowledge as experts in psychology, and which hopefully has also been validated to some extent using potentially causal discovery techniques, conditional independence tests, asymmetries, and so on in the cause-effect relationships and so on. But unfortunately, at the moment, we really don't use it in psychology, in spite of the fact that it's really a key component of human intelligence. We do a lot of reasoning that's cause and effect. It's also what we're concerned with primarily as scientists, is understanding the cause-effect relationships in the world, the causal mechanisms that underpin a certain phenomenon. But unfortunately, causality in social science has had one of the oddest histories, one of the oddest literatures in all of academia. Causality is generally considered to be taboo. I've had my own experiences with psychologists when I've sort of brought up maybe we can do some causal inference or causal discovery. The response has been overwhelmingly negative in some cases, but not really with any well-structured argument, more a general sort of distaste or dislike. And that's why I think this word taboo is kind of particularly appropriate in this case. And it's kind of a shame, especially because we kind of use it anyway. When we do SEM, structural equation modeling, we're kind of doing the linear version of this causal inference. But we're not really doing it properly. We're not kind of validating it using causal approaches. We're not really clearly stating our assumptions, the causal assumptions that are sort of associated with this model. We're just kind of doing it, pretending it's not causal, saying that everything's about association, and then kind of getting away with an awful lot of very loose reasoning. And multiple regression as well, even though it may not seem like it, has its own kind of causal interpretation as well. So we have to be really careful about how our analyses interact with the structure that's contained within the data that we're using. And there's this quite complicated interaction between the two. We can't simply just use any data with any structure. We really have to consider where the data comes from, the data generating mechanism that led to those observations. And this, going back to this adage, correlation is not causation. It's not fair to just rule out causal inference or causal techniques just on the basis that maybe we just have a cross-sectional data set. Indeed, longitudinal data may actually make things harder for us in some ways. Maybe not if we keep everything equal, but if we sort of sacrifice maybe some high-quality cross-sectional data sets with the view that longitudinal is the only thing that can make things causal, this may not be the only way of doing things, and it may actually make our lives more difficult. So what I'm going to talk to you about now is a little bit more involved. I understand it's maybe not to everyone's taste to talk about things in this sort of level of detail, but I think it's worthwhile doing anyway. So I'm going to sort of present to you here, this is kind of like a probabilistic graphical model, or you can think of it like a structural equation model. One here is really supposed to represent like an offset, an intercept, and x1 to xk minus 1 are the variables in our model, and y is the dependent variable or the outcome variable. And so this model here actually represents kind of what we're doing when we do multiple linear regression. We have a series of independent variables here. We have an offset or a y-intercept here, and then we have the outcome y. And I want to start with this model because it's super basic. I want to assume that everything's linear, because these ideas do actually generalize to non-parametric, non-linear, arbitrarily complex processes. But if we stay in the linear domain, it'll be easier for me to sort of talk about these for now. And we're going to assume that there's sort of these effect sizes or path coefficients on each of these sort of arrows here. And when we undertake a multiple linear regression, our goal is really to estimate these path coefficients here. And so what I'm going to do is I'm going to cheat a bit. I'm going to generate data artificially so that I know the true values. And I'm going to use a big data set. And then I'm going to see if I can recover those values using multiple linear regression. And so the code is quite straightforward, but essentially I generate data according to this structure here. This is almost like a representation of our psychological theory that we have, maybe the x1 through xk minus 1 of these high-level semantic concepts that are maybe independent. We assume to be independent of each other. We have this variable, outcome variable of interest. And again, we want to see if we can estimate these thetas correctly. And indeed, we can. And you know, for instance, the theta 0 here, the offset term, the true value is 3.3, we estimate 3.31. This theta 1 linking x1 to y is 0.1, we estimate it as 0.11, and so on. So this does a fantastic job. We show that indeed we can recover the true structure using multiple linear regression. So that's reassuring, but it turns out that this is only really the case because the relationships were all linear for a start. As I said, I'm going to continue assuming that for now, but mainly the structure was trivial. There are very few, I think, phenomena in psychology where we can confidently argue that the variables of interest are all independent and sort of independently related to y in this kind of simple structure. So what I'm going to do now is I'm going to keep things linear, but I'm just going to slightly increase the complexity of that graph, the underlying process, the theory that we might have as psychologists. And so let's look at this graph here. So here we have a few more variables. We have x0, x1, and y, but we have this also x2, x3, x4, x5, x6, x7 here. And if anyone's familiar with SEM or even path modeling, you know, you have sort of these effect sizes associated with each of these paths. And let's say that this is how our theory looks like. This is a representation. This is what happens when we go from our psychology theory and we try to represent that mathematically or specifically as some kind of graph. In this case, it's what's called a directed acyclic graph. And let's say, just for the sake of explanation, that the thing we're interested in really is the effect of x0 on y. So this variable here, what is its effect on y? Now, one thing you could do is just chuck this all into a linear structural equation model, but I'm not going to let you do that. Well, I'm going to say that you can't do that for now, because it's kind of a simple way of doing it, and it only really works when everything's linear. So instead, let's just think, how would we actually get the effect of x0 on y? What variables would we include in a multiple linear regression? Would we include just some of the variables here? Would we include all the variables here? How do we actually get the effect of x0 on y? The solution is actually non-trivial unless you know something about causal inference, and this is why I wanted to encourage people to engage with sort of this whole, you know, correlation is not causation thing, engage with that more seriously and see how far we can take these things. And also to recognize that whenever we have our theory, there is always going to be some assumed structure, even if that structure is sort of very vague and doesn't have very many assumptions, like maybe we just have a fully connected graph where we just let everything kind of cause everything else. You know, there are ways to reduce the number of causal assumptions, but nonetheless, we still have to go from our theory into some kind of graph. And maybe if we're lucky, it just looks like this, and then, you know, there's not as much to worry about. But in reality, it's going to look like this or more complicated than this. So it's really worth understanding how we can use multiple regression in cases that look like this. So again, let's say we're interested in the effect of x0 on y. And again, if anyone's familiar with path modeling, we can actually read this from this plot here. The effect of x0 on y is simply -2, this path here, times -1, this path here, and that equals 2. So the true effect can be read off from this graph just like that. So the true effect we're interested in is 2. The question then is, how do we get this true effect using multiple linear regression? So if we include only the variable of interest, so we have y equals c, some kind of intercept term, plus a, the coefficient, times x0. It's just basically just including x0 and y in our linear regression. Then the estimate for the effect of x0 on y, the coefficient on x0, is 1.28. Now, it could be worse, but 1.28 is clearly not 2, and you can trust me that I've used enough data here. I think it was 5,000 samples. You know, collecting more data isn't going to take us much closer to 2. It's going to really converge to some value close to 1.28. So this is a biased estimate, and if we have more p-value, more data, then we're just going to get more and more confident that this is the true effect and that it's non-zero. So if you sent this to a reviewer, they might say, well, what you should look at, rather than just having this very simple model with only x0 in as a variable in the model, you should look at the bivariate correlations first. So this here is a list of the bivariate correlations, x0 on y, x1 on y, and so on. And what you can see is that they're all highly, highly correlated. Some of them negatively, but they're all very highly correlated and they're all highly statistically significant. So just based on this table alone, I think a reviewer would argue, well, you absolutely have to include all these variables. They are all very important variables, and you can't ignore them. You can't leave them out of the model. They're all relevant for explaining variation in Y. So if we do that, we actually get an estimate of the effect of X0 on Y of minus 0.01, or we could just call that 0. It's very close to 0. Now, this is much worse than before. So including all these variables has made things much, much worse. We're further away from the true effect of 2. You might actually get a false negative here, potentially, depends on how many samples we have. But yeah, so that's obviously not an option. And I think even though it's very common for reviewers to maybe ask you to include any variables that are sort of highly correlated just in a bivariate sense, it's really not the right thing to do, because there's an interaction between our linear regression and the actual underlying data generating process. Another option might just be to include X0 and X1. They both look like they're kind of en route to Y. But if we do that, we actually get an even worse result of minus 0.94, so minus 1. So now we've actually flipped sign. We're doing really, really badly, and we're pointing in the wrong direction. And maybe this is already familiar to some of you, that we shouldn't really be including mediators as control variables in our models, because it kind of blocks the flow of information that we're interested in. We're interested in X0 and Y, but if we include X1, it's kind of like stopping X0, and it gets in the way, because we end up sort of holding X1 constant. So none of these approaches worked at all. Apologies for the over-the-top slide here. They were structurally misspecified. So in other words, our model, our multiple linear regression, did not work in a way that was representative of the underlying structure, or not in harmony with the underlying structure. So our estimates, our associated estimates, were completely wrong. And so to deal with this, some little rules, some simple rules are quite handy for deciding whether or not we should include certain variables or not. There are only 3 rules. I'm not going to go through them in too much detail, but suffice it to say there are sort of 3 kind of canonical structures in this graph. One is this chain. So we have A, B, C. So A causes B causes C. And if this middle variable is in green, it means it's been included as a control variable or an adjustment variable in our linear regression. And what you can see is that if we're interested in the effect of A on C, including B as a control variable blocks the path, which means that we can't estimate the effect of A on C. In this structure here, this is called a fork structure. So we've got B causing A and B causing C. It's sort of going out from the middle. And again, if we include the variable B here as a control variable, we again block the flow of information, the flow of statistical information between A and C. And then finally, we've got this collider structure here, where we have A causing B and C causing B, where here actually it doesn't need to be included in the model. It's not green, it hasn't been highlighted like these others have. It's not green, so it's not in the model, which means that that path is already blocked. So here you don't need to, if you wanted to stop that path, you shouldn't include this variable in the model, because it's already closed. So using these rules, we can actually look at this graph and see whether or not any of these variables we should include or not include. And as an example, this chain structure here is seen exactly in this mediation path here, where we have X0 mediated by X1 to Y, is this same as this top structure here. And we can see that if we're interested in X0 and Y, we shouldn't include X1, because doing so would block the path. So we should leave X1 out of the model. And indeed, we should also leave, we should include one of these 2 here. So I was going to say there was another path here. This is actually a spurious path. This is confounding to the extent where it's not a causal path. It's not an indirect effect or a direct effect from X0 to Y. It's a spurious path because X2 is pointing into X0. So there is no causal path that leads from X0 through these variables to Y. And so what we really want to do is stop this flow of information here, because this flow is going to bias our estimate of the effect of X0 and Y, because actually, if you look at these rules here, there's nothing stopping the flow of information to go through this fork here. You can see if this was black, it would be an open path. So we get flow of information from X0, X2 to X3. Then we have another chain here. So again, information is flowing this way here. So This is actually a form of backdoor adjustment. There are other techniques, like front door adjustment is another one. If you undertake backdoor adjustment, you can use these rules to identify the set of adjustment variables or control variables to include in your linear regression, such that you isolate the effect that you're interested in. So again, if we're interested in the effect of x0 on y, according to these rules, we want to block this backdoor path through x2 and x3, and we can do that by including x2. We can do it by including x3. Both of those block this path, or we can include actually both x2 and x3 here. One thing to bear in mind is that when we have our linear regression, we're not only going to get coefficients on x0, which is the one we're interested in. In this case, we get 2, which is perfect. It's an unbiased estimate of the effect of x0 on y. But we're also going to get coefficients on the other variables that we've chosen to include based on the choice of adjustment set. But these variables may or may not be interpretable. So for instance, if we include x2 and x3, then the effect of x2 on y will be represented by the coefficient on x2. But if we include x3, then that effect will be blocked, in which case the coefficient on x2 will be probably close to 0. And the coefficient of x3 can be interpreted, and it should be close to 2, the true value, the true effect of x3 on y. So we don't only have to be careful about the interpretation of the main effect of interest, we also have to be careful about the interpretation of the coefficients on the other variables as well. So something to really bear in mind. Now, the benefit of this sort of approach, and obviously I've only gone through it at very, very top level, and I've sort of skipped through it very quickly, but these approaches are general to the extent that they can be used in non-parametric situations and with arbitrarily non-linear effects. And once we have these techniques and we want to extend them to the general scenario, the general problem, we can specify tau, for instance, as our effect of interest, and we can express it using what's called do calculus or do notation. And here, as an example, what we're interested in is the effect of x0 on y, and that effect can be denoted as the difference between when we set x0 to 1 and when we set x0 to 0. In other words, the probability of y either being 1 or 0, or the probability of a particular value of y given that x is 1 or 0. We subtract the difference, and then we take the expectation over our values for y, and that will give us the average treatment effect. And each of these sort of expressions here, p of y given do x, so do here represents what's called an intervention, which means we set x0 to 1 in this case, or to 0 in this case, which removes the influence from the other nodes. And so this expression is kind of like it conveys to us that we've done an intervention, that we're interested in a causal quantity, not just a statistical or associational quantity. And we can actually represent this using, say, this expression here, where we've got the integral, which is a form of the expectation for p of y given do x. And here we've got y, x, and z, where z is the adjustment set, the variables that we need to block the backdoor paths and to isolate or identify the effect that we're interested in. So again, I'm not going to go through this in any more detail than this. There's a huge literature on the specification of these. This is kind of the problem of identification. And in some situations, it won't be possible. In some graphs, it won't be possible to estimate the effect that you're interested in using observational data alone, particularly if there are unobserved confounders, so third variables, for instance. And so because these techniques are general, we can also combine these approaches with our favorite techniques from machine learning, or our favorite ensemble from machine learning, in order to not put any wrong or overly simplistic functional restrictions on our model, so that we can combine the best of our knowledge in a structural sense, but also the most flexibility in terms of a functional sense. So this is where the combination of machine learning and causality combine. The combination sort of occurs so that we can get the best of both. And the result can be combined with techniques from semiparametric theory to derive confidence intervals. So we don't just end up necessarily with a point estimate for this tau, but we can also get statistical inference from it, still get confidence intervals, p-values, all of the things that we're used to or we might want to do. And at that point, we might want to look at sensitivity analysis, which I briefly described in the introduction as part of this pipeline. And this is an example taken from a paper by Van der Laan, Gruber, and others. Actually, this was from a talk where they covered, I think, a study. So this is a slide from a talk. And here, just to give you an example, this effect that's in this oval border here, it might be our original effect estimate and the confidence intervals for that estimate. And then each of these other effects represents some perturbation of our model, some level of misspecification of our model, or possible misspecification that we don't necessarily know, but could be the case. So for instance, if we assume that this is the graph, but maybe it's slightly different, maybe there's an unobserved confounder that we haven't accounted for, we could represent that by creating that model and running that model, and then see how that effect changes. So along the x-axis here, we've got sort of different multiples of that bias that comes from this misspecification. So this 1 times bias here might be the particular misspecification that we're interested in. We simulate that by misspecifying our model on purpose, running the data through it again, and then we get this effect here, which is sort of this much different. And then we can say, well, we can look, well, what if that effect was in the other direction? Or what if it was twice as impactful? And so you can build a real understanding for to what extent your model will be misspecified before, for instance, you get to the no effect regime. So for instance, if the, in this case, it kind of shows that between 4 and 5 times the amount of plausible bias that you're willing to sort of acknowledge is possible in your model, you actually start your confidence intervals start overlapping with 0. So that would be you'd need 4 or 5 times as much bias to get a null effect. People have talked about this at length in other places. There's a great tutorial introduction by Brady Neal. He actually has his own book on causality as well, gives an example where he shows that for a relatively realistic situation, you can get up to, well, I say up to around 407% error. And really what I wanted to do is include this slide just to convey to you that these effects can be very serious. The problems associated with functional misspecification can lead to some really wild estimates, which makes them almost impossible to interpret. Now, the whole point of sensitivity analysis is to acknowledge that sometimes we get things wrong. And so, you know, this effect here is actually based on a set of assumptions that may be very strong. You know, for instance, we assume that this is the correct graph, and we hope that we've done enough to validate that graph such that it's plausible. But what if it isn't? You know, this is always a possibility. In that case, you know, these effects could be really a long way off. But this is partly why I think it's so important that we acknowledge the potential for this bias, and we do everything that we can using all the available recommendations and techniques from the fields of causality and potentially also machine learning in order to really do a better job than what we're doing already, which is really just almost blindly specifying this model, picking from a number of different models that are similar based on their predictive capabilities. So we use fit statistics, which is not really a good way to validate causal structures. And then we just run the analysis and report the effects, often as associations rather than causes. But it's kind of ironic, and it's a bit of a conflated approach because, again, you can't use fit statistics, which are purely sort of predictive. You know, how well does this explain the data in order to validate your causal structure? So that brings us back to the complete pipeline again. One thing I haven't talked about is causal discovery, and I'm not going to talk about that today. But I've kind of talked about how we can take our theory to a graph like the one that we specified before. And then once we've got that graph, we can specify a target parameter of interest. For instance, the average causal effect we had between x0 and y. And that target parameter can be specified very exactly for a given graph, so that it's easily repeatable, and it's very specific, and it's not ambiguous in any way. And we can undertake estimation using machine learning approaches here. We can use semiparametric statistics, which we haven't spoken about, to provide confidence intervals and p-values. We can run sensitivity analysis to check how sensitive our graph, our misspecification, how sensitive our inference is, how sensitive our estimation is to misspecifications in the graph, or even maybe some kind of limitation of our machine learning models. And then finally, we can do our interpretation. And you can see that this is a very involved process. And because this approach has kind of been developed in tandem, this is my own sort of interpretation that I'm putting together, but it's not far off the proposal from Mark van der Laan. And Mark van der Laan talks about this sort of whole process similar to this, and acknowledges that it's a lot of work and it is difficult. He says it requires a reasonable understanding of statistical theory, but nonetheless, it is a worthy academic enterprise. So, the value of really getting robust cause-effect estimates, it's huge. It's so valuable. But of course, there's no free lunch, as it were, and we should expect that this does require a lot of hard work to make sure that our estimates are, as close to unbiased as is reasonable given a set of assumptions, rather than doing what we do at the moment, which is just to sort of specify our models relatively blindly and let them be driven by arbitrary and simplistic assumptions. And so Mark carries on and says, we will open up a new world to our collaborators by actually being able to generate questions our collaborators had no idea they were even allowed to pose. So this, for me, relates back to that whole adage about correlation is not causation. The idea that you can use, an imposition of a graph here to derive causal quantities is often just dismissed as just impossible in social science and psychology. Things are changing, of course, but it's still kind of taboo. And then finally, Mark says, with these collaborators will actually get excited instead of bored to death by another logistic regression model. Maybe something a bit more lighthearted. So, as I said before, the current paradigm, we sort of start with the wrong model. This is either because we've assumed linearity or because our structural form is not well validated. We sort of guarantee ourselves some significant results because, again, if we just have enough data, we guarantee significance. We submit it to reviewers. They will either accept it straight away or they'll ask us to select from a family of equally sort of incorrect models, more linear models potentially, maybe even some models with sort of overconfident assumptions about the functional form, or other models that are sort of overconfident about certain structural relationships which have not been validated. Then we go through the loop all over again until the reviewers are finally satisfied, which again results in non-correcting science or non-self-correcting science, which confirms the prior expectations or beliefs. It isn't really a scientific endeavor. And so with the new pipeline that I'm proposing, what I'm hoping is that we move more towards something like this. We start off with the right model. Obviously, that's a very loaded way of describing it, but what I mean is a model that does not start off with a set of extremely unreasonable, implausible assumptions, such as this is fully linear, we haven't tested the causal structure, we're assuming it, and we're developing it with predictive fit statistics. So we've done, what we should be doing to start off with a model that's quote unquote correct or right. We get results which are hopefully unbiased, as close as can be. We've got sensitivity analysis in here, so we understand when it may or may not become significant or non-significant based on a sort of a degree of misspecification. We submit this to reviewers. Again, maybe they disagree. They can accept it straight away, but they could still disagree and ask us to maybe validate that structure again and argue why it's correct. But regardless, rather than continuing to sample models from a pool of incorrect models, we just sort of refine this correct model. Maybe there's something that we kind of missed out or that we could improve upon. And so this process instead results in self-correcting science, which does actually test our beliefs and our expectations rather than simply confirming them. So where do we start? Sometimes we don't know the graph at all. Maybe it's a new area. We haven't done much causal discovery. We're sort of starting from scratch, as it were. And what if we just want to explore? What if we're really sort of admittedly ignorant about a particular problem and we don't know what to do? We can't seriously engage with that pipeline yet. That's absolutely fine. As I said, it's a lot of work, and it shouldn't be expected that we can just go all the way from the start to the end of that pipeline all in one go in one project. It's a really long process, and that even that first part of it, that theory, causal discovery, data, and graph kind of block is all about exploring the data and validating our theories, developing our theories as well. And so we can do things like just look at associations to begin with, just see which variables are predictive, and then try and maybe confirm that they might be causal using structure discovery techniques. And it does all sound like a lot of hard work. And in general, we can carry on as we are. We can continue publishing under that sort of increasing pressure to publish, a very competitive world in academia, but it is not necessary to move the field forwards. And other fields are already doing it. So for instance, Mark van der Laan works in biostatistics and epidemiology. There are people in psychology and social science that are already starting to adopt these techniques. So to that extent, you know, let's not get left behind. Let's update our arsenal of techniques and start engaging seriously with the fields of machine learning and causal inference, causal discovery, in order to start making that pipeline a reality for us as part of our research. And if you're interested, so I now work at University of Lausanne as a doctoral assistant for Professor Peter Hilbert, and part of my responsibility there is to provide some statistical advice. So if you want to get in touch, then please do. And again, I think when you start to look at all of these problems in psychology, the replication crisis, all the purported causes of the replication crisis, it can be quite overwhelming and quite depressing. You know, trust me, because I've been there in that regard. But actually, I think we should spin this in a different way. And I think it's really helpful if we see this as an opportunity. You know, in some ways, I'm lucky because I'm able to work on this in this really exciting time where we're kind of changing our approach to analysis. And I'm hoping it's not just the emperor's new clothes. There's a lot of hype around machine learning, but if we're realistic about what machine learning and causal inference can and can't do for us, then I think actually we've got a lot to gain from those areas. So yeah, please get in touch if you're interested. So in terms of the summary, as I said right at the beginning, when was the last time we had conversations about state of the art in statistics? You know, we're maybe reading psychology papers all the time, but we're not spending much time sort of checking up on recent papers in philosophy of science or statistics. And so we really need to keep abreast of progress in those fields as well, because we absolutely depend on those fields in order to, they're almost like the gatekeepers for our psychology. They're the thing that takes our passion, our interests, and our domain knowledge and starts to turn it into something scientific and rigorous. So yeah, we need to keep abreast of the progress in these areas. It's almost like a chain, and at the moment, maybe these sort of particular links in our chain for psychology are sort of a bit weak at the moment. And yeah, just on that note, how can we be sure nothing in our research chain is broken if we never check, if we just keep doing the same analyses that we've always done and rarely sort of question it? That's not a scientific approach, and it's likely to not end very well. As I said, psychology is facing some fundamental barriers. Let's see this as an opportunity. But at the moment, you know, if we carry on sort of misspecifying our models, it does result in some rather meaningless effect sizes that are very difficult to interpret. And this comes as a general lack of analytic rigor and due process. So as I said, we want to combine machine learning for correct functional specification, dealing with that non-linearity, arbitrary complexity. And we want to combine that with causal methods for correct structural specification of our models. And altogether, we hope for a research and an analytical pipeline that's sort of relatively complete and rigorous, and that we can come back to at any time to improve any particular sort of component of it. And so in terms of my open projects at University of Lausanne, you know, I'll be sort of recommending this pipeline to other researchers and hopefully developing it into something more concrete that we can submit as some kind of tutorial paper for psychologists to engage with. I want to thank these different collaborators. You know, they've been very patient with me, and you know, I've wanted to sort of change how things are done in psychology, and that desire has kind of been shared to very varying degrees by these other collaborators, and they've really facilitated my work in that regard. So without these collaborators, that wouldn't be possible. And I hope to add to this list, you know, as we sort of collaborate more as part of this department. And yeah, I very much look forward to working more on these methods. So that's everything from me. And if you have any questions, please feel free to ask or send me an email.